In today's video, we'll cover quite a few topics, but this is just to give you the general broad strokes on how to deal with derivatives, right? So there's a few sort of subtopics that fall under derivatives because it's a big general topic, and we'll try to cover sort of the rules, the general rules that that govern these derivatives. So first of all, we'll look at the derivative of a quotient. So this general form just describes the derivative of any function f of x divided by any function g of x. Okay, so I'll just represent that with f of x divided by g of x all prime. And for this, f of x and g of x, like I just said, can have any values, right? So you're not restricted on the values of f of x and g of x. And we'll see that when we explore a few examples, right? So if you have the quotient of two functions, right? The way you solve this derivative is you first take the derivative of the numerator, right? So in our case, our numerator is f of x. So you take that derivative, you multiply that by the denominator, right, which is g of x. You subtract that with the numerator, right, which is f of x, multiplied by the derivative of the denominator, which is g of x prime, right? And all of that's divided by our denominator squared. So this is the general rule that applies to all quotients, right? So whatever the values are for f of x and g of x, this is the general rule that basically governs those types of derivatives, right? So that's for the quotient rule. Looking at the product rule, so the product rule tells us now that if we have, right, so let me just copy what we did here before. If we have, rather than the quotient now, let's say if we have the product of two functions, f of x and g of x, okay? Once again, f of x and g of x can be any functions, right? So this is the good thing about these general forms is that you can apply them to basically all sorts of functions, right? So if you have the general form f of x multiplied by g of x, so the product of two functions, the rule tells us that that is equal to the derivative of the first function, right, which is f of x in our case, multiplied by the second function plus the first function multiplied by the derivative of the second function. So once again, this applies to any function, right? Any function f and g of x that are multiplied, right? So if you have any product of two functions and you're trying to find the derivative of that product, you can use this general product rule. Okay. So next, if we look at, well, there's a repetition there. So I guess the next point will be, so what happens now if you're looking at logarithmic derivatives? So this would be the derivatives of derivatives involving logarithmic functions, right? And obviously, you remember that logarithmic functions fall under functions fall or rather they cover, in most of the examples that you'll be looking at, two main forms, right? So this is two main forms. The first form is, the first form is when you have the natural logarithm. So you have ln of some function f of x. Right, so that's just one specific form. And remember that that is just equal to the logarithm of f of x in base e to the base e, right? E being a specific number in when you look at logarithmic functions, right? And you know what the value of e is. I believe it's 2 point something, right? So that's a specific case of logarithmic functions. The second form is the other general case, which really covers, this other general case covers the first case rather than the first form, and that is the logarithm of now the same function f of x, but now to the base a, and a can be anything, any positive value, right? So in most of the examples that you'll be looking at, those are the two main logarithm that you will be encountering, right? And obviously, you guys, you can always go back and forth in between the two forms, depending on what you're trying to achieve. But if you're looking at specifically the derivative of these functions, these are the two forms that you'll be encountering. So for those two forms, the general, so first we'll derive the general form, and then we'll look at the specific case of the natural logarithm. So the general form tells you that if you have the logarithm of a function f of x to the base a, right? That is just equal to the derivative of the function f of x, right? Divided by the original function f of x. And in the denominator here, multiplied by ln, right? The logarithm, the natural logarithm of a, right? So now if we have the special case of the natural logarithm, and you're trying to find the derivative of some function f of x to the base e, then that is just equal to the derivative of f of x, right? Which is the same as in the general form, divided by the original function, but now multiplied by, because in our case, a is equal to e, ln of e, right? And ln of e, remember, is just 1. So that can be simplified to be the derivative of f of x divided by f of x. Right? So that is the special case of the natural logarithm. So then, since you have that, you can sort of solve any logarithmic expression, and you can find its derivative quite easily using those two forms, right? So, and also, just to mention, these logarithmic derivatives are also very helpful in cases where you have you're trying to find the derivative of some function f of x to the exponent of some just So these logarithmic derivatives are specifically helpful when you're trying to find the derivative of some function f of x to the exponent of g of x, right? So when you have a case like this, typically what you do is, right? So you're trying to find this derivative. What you do is you let some y be equal to this f of x to the exponent of g of x. And then you introduce, right? You introduce the natural logarithm. And the reason why you introduce the natural logarithm rather than the more general form of logarithmic functions is that because its derivative, as we've seen here, is a bit easier than the general form. Because with the general form, you still have to deal with the 1 over ln a here. And it's when you're doing very long calculations, you'd rather simplify it the most, right? Plus it works out anyway, so I don't see why you would have to use the general form to solve your problem, since the natural logarithm just works fine, right? So this is what you would do. You would introduce the natural logarithm on both sides. Take and then obviously you remember your rules for for logarithms in general is that if you have ln of f of x to the g of x, this exponent g of x can come out of the ln function, right? So you can take it out of the ln function, and it just becomes g of x now multiplied by f of x, right? And when you have that, then you can refer back. You basically have the quotient, sorry, rather the product of two functions, g of x multiplied by ln of x, right? So now, if you're trying to solve this, you take the derivative on both sides, right? So if you take the derivative on both sides, what you get is on the left-hand side, you have y, sorry, ln of y, and the derivative of ln of y is just 1, right? Remember, it's not what, well, it's not 1. It's basically y prime, right? It's the derivative of y divided by y, right? If you look at our formula for the logarithmic the natural logarithm of the derivative of the natural logarithm of some function f of x. So in our case, f of x is just y, right? And y, remember y, because we let y be a function. Y is a function of x. So you can't just say that it's equal to 1, right? Because it's a function of x, so you need to make note of that, right? So then you would basically, when you derive the left-hand side, you have y prime over y based on the formula. And on the left-hand side, sorry, on the right-hand side, you would have, because you had the products, now you would use the product rule. So you would take the derivative of the first function multiplied by the second function plus the second function multiplied by the derivative of the first function. Oh, sorry. It's the second, sorry, it's the first function multiplied by the derivative of the second function. Right. I hope I said it right. The first function multiplied by the derivative of the second function. Right. And then obviously, since you have y prime over y, you can take the y to the, you can multiply by y on both sides. Then you have on the left-hand side, you have y prime left multiplied by this entire big bracket here, multiplied by, equal to the entire brackets multiplied by y. And that is your general form, right? So this is another case where you would use logarithmic functions to find the derivative of your function, of your specific expression, right? And that expression is the case where you have a function to the exponent of another function. Right. Okay, so then next we'll look at the derivative of polynomials. Right. So for this, we also have a general form for this, and the general form basically tells us that if you're looking for the derivative of some function, right, any function f of x to the exponents that is raised to the exponents of n, and obviously n can be any value, right? But more specifically, values greater than 0, right? So basically, a function f of x raised to the value raised to some constant n, where n is greater than 0, the general rule tells us that what you do is you take down the exponents, which is n, you multiply that exponent with the derivative of the function, right? Which is f prime x, right? Multiplied by the original function, right? But now to the exponent of n minus 1. So you subtract 1 from the exponent, the order of the function, right? So that is the general form. We'll look at a few problems as we move along, but this is just to sort of introduce the concepts. Now, this can be applied to any function f of x. So, for example, let's say you had the case where you have the derivative of some function f of x equal to, let's say, x to the 15, for example, right? That is a function, f of x. In our case, our f of x is just x that is raised to some constant 15, right? The general form tells us that we take down the 15, we multiply it by the derivative of our function, which is just the derivative of x, which is just 1, right? Multiplied by the original function, right, x, but now to the exponent of 15 minus 1, which is 14. And this can just be simplified as 15x to the 14, right? So that is for polynomial expressions. Next, we look at the exponential functions now and how you find their derivatives. So for the exponential function, we also have a general rule. So the general rule tells us that if you have some constant, let's call it a, that is raised to the exponent of some function, or in other words, you have, I don't want to call it the opposite, but you basically have uh, um, what we did for the polynomial case, but now in reverse, if you want. So now instead of the polynomial being, or rather the function, let's just call it the function in general. It, instead of having the function raised to some constant n, now we have a constant raised to some function f of x. So for that case, the general rule tells us that this derivative is equal to the original function, which comes back. So basically, a to the f of x comes back, right? Multiplied by the derivative of the exponent, which is the derivative of f of x, multiplied by ln of the base of the exponent, so ln of a. Right? So this is our general form. Now we have the special case where a is equal to e. Right? So in the special case where you have a is equal to e, you have that, let's say you have e to some exponent, to the exponent of some function f of x. The function f of x can be anything. This is just equal to e to the f of x multiplied by the derivative of f of x multiplied by ln of e, ln of e, and that it can just be simplified as e to the f of x multiplied by the derivative of f of x, right? Multiplied by 1, basically, because ln of e is 1, and that just can be omitted because this whole thing multiplied by 1 is just equal to the same thing. Right. So that is this for the special case where a is equal to e, right? And finally, the other case we'll be looking at is where you have the derivative of trigonometric functions, right? So, and obviously there are multiple trigonometric functions, so we'll just look at a few of the general ones. So you have sine of x, the derivative of sine of x in general is just equal to cos, right? Cos of x. Or if you want to write it in a more general way, let's say we had some other function. It can be x, it can be, well, let's just write it as the general, in the general form of f of x. Okay, so it can be sine of any function f of x. That is just equal in the general form, right? It's equal to cos of f of x, but now multiplied by the derivative of x, right? Sorry, the derivative of f of x, right? And for the special case now, because this is the general form, for the special case where you have f of x being equal to x, then this just becomes, right, the derivative of sine of x, which is just equal to cos of x, multiplied by the derivative of our function f of x, which is x, so the derivative of x, which is 1. So it's basically 1 multiplied by cos of x, so which is just cos of x. So that's for the special case of that. And if we have, now let's look at what happens if instead we have the derivative, the general form of the derivative of cos of x, of f of x. Then that is just equal to, once again, remember the derivative of of cos is just negative sine, so it's equal to negative sine of f of x multiplied by the derivative of f of x, which in the special case where f of x is equal to x, right, you have the derivative of cos of x, which is just negative sine of x, right? Negative sine of x multiplied by the derivative of f of x, which is just the derivative of x, which is 1. So this whole thing can just go away. And then you have negative sine, which is what you guys clearly remember. So now when you have the special case of the derivative of the derivative of tan of x, or rather, let me call it tan of f of x, right? That is basically equal to the derivative of, remember, tan is just sine, right, over cos, right? So it's basically sine over cos sine over cos of f of x right? That's the derivative that you're trying to find. And obviously, if you look at this, you have the quotient of two functions, right? So you can refer back to the quotient rule, and this will just be equal to, right, the derivative of sine of f of x multiplied by cos of f of x minus sine of f of x multiplied by the derivative of cos of f of x. Right? And all of that is divided by cos of, rather cos squared of f of x. So that is the general form. And now if you apply it to the special case of where tan, rather where f of x is equal to x, what do you get? So you basically have tan, the derivative of tan of x, which is equal to the derivative of sine of x divided by the derivative of cos of x, which is just equal to the derivative of sine of x multiplied by cos of x minus the sine of x multiplied by the derivative of cos of x, all divided by cos of x squared. And if you refer back to our original derivatives for sine and cos, you will get that in your numerator, you'll have the derivative of sine is just cos, so you have cos times cos, so that's cos squared of x minus sine of x, right? Multiplied by the derivative of cos of x, which is just negative sine. So it's basically negative, negative, so that becomes positive sine squared of x, because it's sine multiplied by sine. And this is all divided by cos squared of x. And remember from your trigonometric identities that cos squared plus sine squared is just 1. That's 1 divided by cos squared of x, which is equal to sec squared of x. So if you remember, if you look at your original identities, you can see that the derivative of tan of x is just equal to sec squared of x. So this is where it comes from, right? It comes from this general form here. And that's how you would solve it. Right, so that is it. And I'll try to look at a few problems as well next, and then that you'll be able to find that in the next video. So please don't forget to, if you really like the video, just give it a thumbs up, and yeah, just subscribe to the channel so you can have more of these videos. Let me know what you think about it as well, because it's a different kind of video from what I usually do. So just let me know and see if you like it and if you have any suggestions. Right. Thank you.